I would like to welcome you all to the Mathematics Institute. My name is Alain Gorielli, and I'm in charge of the public lecture series for the Institute. Before we start the event, let me remind you that, as usual, the green side indicates the emergency exit. I also want to acknowledge a sponsor that you can see there, Eschermatics. They're the sponsor of the whole Oxford Mathematics lecture series. Eschermatics is a leading quantitative-driven electronic market maker with offices in London, Singapore, and New York, and we're very grateful for the support. Now on to the main event. As you can see, or as you know, or as you can feel in the air, tonight is a very special event. It's actually co-organized with the Clay Mathematics Institute and Oxford Mathematics. As such, it will be a little bit different from the usual format. The public lecture today will be followed by the presentation of the Clay Award for Dissemination of Mathematical Knowledge. I call it CADOMC for sure. So you will have the distinct honor to be part of the event and the presentation, the award ceremony for the CADOMC. And since we want it to be directly after the talk, we will not take a question today. We'll go directly into the award ceremony. Nick Woodhouse, who is the former head of our department and the current president of the Clay Mathematics Institute, will give us a full description of the awards and of Professor Penrose's achievements. So I will be very brief in my introduction for tonight's lecture. I will just say the following. When you work in mathematics and physics, one sign of becoming famous is that your name may be associated with a theory. We say, oh, the theory, yes, that person made it. Now you realize that Roger is in a completely different category when you see the partial list of theories that has been named, that either has name or that naturally associated with him. For instance, you'll find the twistor theory, the notion of spin network, cosmic censorship, Weyl curvature hypothesis, Schrödinger-Newton equation, Andromeda paradox, conformal cyclic cosmology, just to name a few. Now it gets even better when your name is used for a famous phenomenon or a theorem. As you probably guess, people don't usually name things after themselves. Well, some have tried, but it usually doesn't work. So for that to happen, for a name to be given to your name to be given to something spectacular, first of all, you have to done something quite remarkable, but you also must have the admiration and the respect of entire community. And again, here the list is quite long, and I'm just naming a few. People in mathematics and physics know about Penrose inequalities, Penrose interpretation of quantum mechanics, the Moore-Penrose pseudo-inverse, the Newman-Penrose formalism, Penrose diagram, and of course the Penrose-Hawking singularity theorems, just to give you an idea. But things get even better and transcend science when your name are associated with things for the public at large, beyond physics and mathematics. And here again, we have Penrose styling that you might have seen coming in, and we'll hear tonight. The Penrose cube that you can buy online. The Penrose stairs, the Penrose triangle. And of course, these last things are closely associated with his contact and influence on the artist M.C. Escher, and is the topic of tonight's lecture. So without further ado, please help me welcome Roger, and let's hear directly from him about this topic.
Well, thank you very much. Yeah. Well, it's a great pleasure and an honor for me to be able to address this very distinguished audience here. And I should explain the title, first of all. It's a book which I'm supposed to be writing, and this is a way to get me started on this book. I keep telling my publishers that I'm way getting through, and it'll be nearly finished. I haven't actually started yet. But this is the start in a certain sense, because I had to organize my thoughts. Well, I had done that much already, but I had to organize my thoughts particularly. I should explain the idea is to use Escher pictures as an introduction to certain various areas of mathematics. So it would be so that it would be a book for the general public, and you would introduce the ideas by looking at Escher pictures. I found it quite difficult in a way because one of the problems is it's not as though sticking, this Escher illustrates this one illustrates that, this illustrates the other thing. You find that the same picture illustrates about 3 things all at once. And then to try and put these into some kind of organization, I found extremely difficult. At least there's something I can start with. Escher, I think when he was in Italy, he did a lot of prints, lots of pictures in which he, they were sometimes a little exaggerated, but very accurate pictures of scenery and so on, buildings. And I think it was when he visited Alhambra in Spain, and he realized all these incredible Moorish patterns, which he tried to understand what was going on. There were different kinds of arrangements. And then he learnt from a mathematician, I think it was, well, actually, I'm not quite sure who it was, so I better not say. But he got this picture, which shows the 17 different crystal groups, if you like, symmetry groups of the plane, where you have discrete motions, and there are 17 different ones illustrated by these pictures you see here. Well, Escher then developed these pictures in his own unique way, using tessellations of various creatures and so on. I should explain, you see, he did this by, in this one you can see on the outside you've got the ordinary squares or something, and then he will modify them in terms of creatures. This is the sort of thing you have various symmetries. Either you have a translation, which is just a motion without any kind of rotation. You can have glide planes where you translate and you also reflect at the same time. You can have simple rotations. That's the one down here. I don't remember what all the other ones are. Yes, the reflection. That's the other one. So all these different motions combine together to give you the various 17 different groups that you can have. And each one he would illustrate in his own unique way. He was able to economize a little bit, although this one ought to be in color, I think, but I just have a black and white version. So you have to imagine they're all different colors. And the 2 of these different groups are illustrated with the same picture. If you take the colors into consideration, then you have one of them, and if you don't, then you have the other one. So you can do 2 at once. That's the sort of economy that he liked. I shall just show these things rather quickly because I have an awful lot to show you. There's another one, and these groups are illustrated. If you remember what those numbers and letters were and so on, then you can see which one it is. I'm not going to go through that in detail because I have too many other things to say, but I'm just giving you examples of the way in which he illustrated these different symmetry groups. Either with these birds and fish. I'd have to look carefully to see which they are. Probably birds and fish in that case. Or we have, in this case, dogs. And he liked the way that I think they probably have it backwards. It doesn't make too much difference because it involves a glide plane, you see, so you have to turn it over to get the symmetry.
I mean, just freeze.
Is it?
No, it's good, but it doesn't.
Is it okay?
Focus. Yeah, it's good.
Okay. Upside down doesn't make too much difference with some, particularly those ones. And here we see another one, and the groups, as I say, are illustrated at the bottom. I shall run through this rather quickly because I've got far more transparencies to show than I normally would have in a lecture like this. So I think you have to...
Oh, sorry.
Is it not working?
No, I froze it. It's this one. Okay.
That's okay, thank you. I didn't quite see what was happening there, but never mind. They can get very elaborate. For example, with this one, you see the animal, the creatures. I have to see what they are. They're beetles or something of some sort, and their arms all interlocked in complicated ways. But he was good at doing that. And of course, you can different groups. You have to look carefully to see which group it is. but you here have a key at the bottom, so you can tell. Anyway, that gives you a good way to start, because he does illustrate these different symmetry groups, and one can go and talk about what groups are and motions of the plane and that sort of thing. This last picture here has a certain history to it, which I should explain. I once met Escher. I come back to that story as to how I happened to get in touch with him, but I did meet him once, and I came with a certain set of puzzle pieces, which in the shape of the ones that are at the top. 1 minute. I'll put my pointer down somewhere here. At the very top, I had a bunch of wooden pieces. I think they were wooden, and they were the shape that we have here. And the thing was, you have to assemble them so that they cover the whole plane. It was quite interesting because you have to have 12 different orientations, 6 one way up and 6 the other way up, and they all have to be incorporated to cover the plane. And then you can. He did it and wrote me a letter and said, well, he didn't quite see what the principle was, and so I showed him this pattern here. Basically, you have rhombuses, and these little lines mark how you might have this one has to match the next one, and you have to have a modification of the shape, so that one agrees with the other. And this is what it was. This shape was designed so there are a lot of false tries as well, but that's basically. And then I explained how it was done, and I suggested some possible animal, or I think it was a bird of some kind, but rather crude, and I said, I'm sure you can do a lot better than that. And he did produce the picture which I just showed you previously. This is actually the only example he had of what you could call a non-isohedral tiling. You see, it's a tiling of one shape, but the different instances of that shape may not be on equal footing with each other. So although I think the dark ones and the light ones, I'm not sure if it is illustrated that way, but some of them have a different relation to the pattern as a whole. So you see one and another one, and if you move that one to the other one, the pattern doesn't follow it. So you have, that's what's called non-isohedral tiling. It's quite interesting historically because in the famous speech that Hilbert, when he introduced his famous problems at the turn of the 20th century, one of the problems he made was, if you have a three-dimensional shape, is it possible that you have a shape which will tile only non-isohedrally? I'm not sure if that word was used at that time, but that's what he was trying to do. I think he thought that plane shapes were completely trivial, and so there was nothing interesting you could do with plane shapes. But then one of his colleagues or students, I think, Heesch, I think it was, who produced an example which showed that even in the case of plane shapes, this conjecture was incorrect, and that you did have shapes which would only tile the plane, but only in a way which was non-isohedral. So that was an example. But anyway, the picture that Escher made was, I believe, certainly the last watercolor he ever made, which partly due to my slowness in responding to his letters. But never mind about that. Anyway, you can do other things with similar sorts of shapes. Let me just give you an example here. Very similar to some of the ones which did have periodic shapes, but it's not obviously periodic. It maybe extends in some such way, but they're not all the same size. I'm not even quite sure what's involved in the arrangement here. Of course, you can do less symmetrical things still by just having any old animals and things like that. There's no symmetry at all, and of course, many of his examples were things like that. What about 3 dimensions? Well, of course, that's a bit hard to illustrate, but he certainly did things in 3 dimensions. Here's an example of just a cubical arrangement, but and I think this is what I wanted to show here is a sketch of his picture. That's another one there too. So three-dimensional things were things that did interest him. And here we have another three-dimensional picture of these fish. And you can see that, again, it illustrates a symmetry. This is just translation, so it's not so exciting, but it's, as a picture, it's impressive, of course. The only one I know of which illustrates a tiling of three dimensions is this one here. You have these flatworms, or whatever they are, swimming around, and the tiling that you see in the background, they're swimming through it, I mean, just parts of it, of course, is the tiling of regular tetrahedra and octahedra, and they fit together to form a three-dimensional lattice tiling of three space. So you see that he was interested in three dimensions, but it's harder to draw pictures of those things, so I don't know that he did so many of those, or certainly didn't do so many of them. He also explored with distorting geometry in interesting ways. And here you have an example where the building, you go up and it twists around and you find a copy of the building up there, but the geometry is twisted around in some strange way, and this is the sketch for it, I think. So you see examples of that. He rather liked these creatures which he invented because they crawl along like a caterpillar or something, and then they roll up, and they can, when they go downhill, they can roll up and roll down the hill. But these are the steps. I think they do it as they go out the door. But you can see them. Anyway, he rather liked these creatures and made use of them in various ways. But the geometry of the space is distorted in interesting ways too. So, anyway, that's other things in three dimensions. He liked playing with polyhedra and also combinations of polyhedra, such as here you have the two tetrahedra, and there's a straightforward dodecahedron, I think. And that's the kind of thing he played with. I'll give you another example here, which is I have to see what it is because I'm not sure I noticed. See the picture? It's you can probably tell me because you can see it better from where you're sitting than I can. Anyway, these are two polyhedra interlocking each other. I think it's an icosahedron and a dodecahedron interlocking and preserving the same symmetry as each other. And here you have, I think, three octahedra and lizard creatures and various things involved. So, and he's got other ones dotted around like that. So he was quite keen on that idea of showing interpenetrating polyhedra. And the symmetry, this is not the symmetry of the octahedron you have when it's finished. But you see, you can... I should have worked out what the symmetry was before I gave this talk, but never mind. Here we have, again, re-entry. I always like this one because you can see it's a planet of some sort. And the two planets are both tetrahedra, and they interlock, and they don't seem to know anything about each other because one of these is all dinosaurs and things, and the others are some kind of civilized community, and they interlock in that extraordinary way. So I'm going through this rather quickly because you really have to look at his pictures in detail to appreciate all the intricate, the tremendous artistry he has and detail, which is extraordinary. And it needs an examination. Oh, that one seems to be stuck to the bottom here, and that one too. Here we have, this is a stellated, that's the stellated dodecahedron with these pentagrams and passing through each other. And it has the same symmetry as the icosahedron, but it's more interesting in that the faces go through each other, and the polygons also go through each other as well. And I think this is illustrating sort of various kinds of rubbish around here, and then you have this perfect shape in the middle. One of the things he liked doing was exploring the contrast between the image of a three-dimensional object and the three-dimensional object. And here you see this one looks as though it's a three-dimensional object, and the one at the bottom is flat, but nevertheless it's a picture of a three-dimensional object. I mean, they're spheres. This one here is, I guess, a hemisphere or something, but at the top you see a picture. So he's playing around with the picture of the object and the object itself. And he does much more elaborate things of that nature. A striking one is this, where you see in the background these two, I don't know, humanoids or something, which seem to be forming this interlocking pattern, and then they sort of get a bit fed up and walk out of the picture and make friends with each other. So that's one example. He has other examples of the same thing. This I've always liked that one. You see the tiling here of these lizard creatures, or whatever they were, and that could continue as a plain tiling, but then they decide to come to life and they walk around on top of these polyhedra and other objects. Then after having had a stroll, they get back into the two-dimensional picture. It's a paradox, of course, but he loved that kind of thing. There we have a much more elaborate version of the same kind of situation. Also mirrors involved, so you can see the I guess the glide symmetry too, you see, because it's reflected. You have a reflection in the symmetry. With their black and white, and somehow they go around, and you just have to follow it. Right? It's very, very complicated what's going on, because they go through and they're also reflected, and you see the reflections merging with the original creatures. And here's another case where he illustrates two kinds of paradox at the same time. I mean, one of them is this contrast between a picture of something and the thing itself. And here you have a picture of a hand, gets more and more realistic until you think it's a real hand, and that's drawing a picture. And then, of course, it does the same thing there. But there's also a kind of paradox in that the thing being drawn by this hand, and therefore, in some sense, this is it's a product of this thing, and then this is itself a product of that. So you have something which is it's a bit like a Russell paradox, where something is the set which has itself as a member, and you see that kind of thing being illustrated in that picture. I had this opportunity to visit Escher, as I mentioned before, and when I was there, he had this long table. I was expecting when I visited him that he would have a very extraordinary house with staircases going over the window, that sort of thing. And I was rather disappointed to find it was a very neatly organized house with a lovely picture window with the view outside, and a very neat and organized place. And he had this long table, I don't know, about as long as here, and about as wide as that. And he was sitting at one end, and he had two piles of prints. And he said, well, look, this side, this one, I don't have many left, but the other side, I have quite a few left. You can choose one. So I thought, wow. And so I brought the pile over, and I started going through it. And it was a really difficult choice. Of course, some of the favorite ones had already gone. They were in the other pile. But there were a lot of things, and it was difficult to make the choice. And eventually, I picked out this one. Now, he was very pleased when I picked that one, because he said, people don't usually understand that one. And so he thought, since I seemed to understand it, at least I thought I did, I was very flattered that he was pleased with my choice. I should explain it a little bit. Here we have a fish, and you see, as you move around here, the scales of the fish become a tessellation of other fish. And as you go around, if I'm going which way around it is, and you find that one of these fish become this one here. and then its scales become bigger and bigger and bigger, and then one of its scales become the original fish. So it's a bit like that, the two hands drawing each other, but in a somewhat more subtle way. And so it takes a little while to figure out exactly what's going on here. But again, you have this sort of Russell paradox idea. You see the scales are a subset of the fish, but yet the scales become a fish, and then its scales are one of the subsets, one of the elements, at least, of this set of little fish, if you like, becomes the original one. So you have a Russell paradox idea involving sets which are members of themselves, or members of other sets which are members of themselves. It's that sort of thing. It's very much like a perhaps better known picture, the picture gallery, where you see there's a boy, if I've got it the right way around, yes, I think so, a boy over here somewhere who's in a picture gallery. You have to cover up the rest of it really to see that. He's in the picture gallery and he's looking at the picture, and then you follow the picture around and you see eventually the boy is in the picture. So again, it's a sort of Russell paradox kind of thing where the boy is in the picture itself. But it illustrates something else, which was actually explored more by a mathematician, Lenstra, who is a Dutch mathematician in Leiden. And he and a colleague decided, you see in the middle of the picture, Escher didn't quite know what to do. Well, I don't know if that was it or what. He didn't quite know what to do with it. He decided at least that was a place to put his signature. So it's just as though he gave up on trying to fill that thing in the middle. He sort of filled it up in the middle with the other picture, but it's done in a way which you don't quite see that there's anything strange about it. But I suppose it is a sort of singularity in the middle. But here he gave up on the singularity and decided just to have a hole. But what Lenstra and his colleague decided to do was to find a transformation of this picture which would fit inside that hole. And then, of course, there's a hole inside that picture, and so the whole picture goes into that as well. And he made a very nice film of this, where you sort of zoom in on it, and you see the pictures inside itself all the time, and it gives you a very eerie feeling. It just goes on and on and on, with a slight rotation at the same time. But to do this, and I think Escher also used this sort of thing when in it, they use a bit of complex analysis here, because it's a conformal picture, and the conformal, this is of course where one can talk about the mathematics in developing the idea of complex analysis and how the mapping of the complex plane, holomorphic mapping to another part of a complex plane, you always have these things which are conformal, so that angles are preserved, sizes are not preserved. What was that? Oh, I better start that again, yes. Yeah, I tend to knock my microphones off by waving my arms around, but so this is the sort of mathematics kind of lead into, because it relates to the conformal geometry that relates closely certainly to the one-dimensional complex analysis, which is complex. You have two real parameters to describe your complex number, and so that's the normal complex plane. And then when you transform with a complex analytic function, or differentiable, complex differentiable function, then the mapping is one which is conformal. And the Dutch mathematicians made a great deal of use of this in order to make this picture map into itself. You have to do something about making this square outside into a circle to make it fit, but they managed to do this very well. Okay. Well, conformal transformations are also interesting. Escher made use of them here. I hope you can see this one. It's a bit like the tessellations of the plane we had before, but as you work your way down, you see the sizes change. And so it really isn't quite a Euclidean motion, but it's a Euclidean motion where you squash it down. So it's one of these conformal motions which relate into complex analysis, and that would be very nice area to discuss, certainly in more detail. One of the more famous of Escher's pictures is this one here. And here we see one of his circle limits. It's quite curious because I find it very useful to use this picture to illustrate the different cosmologies. In cosmology, you usually make an assumption that the universe is spatially isotropic and homogeneous, and these things, very limited number of geometries you can use, basically characterized by the curvature. The curvature can be positive. There can be more complicated topologies, but there are basically the three types: the positive curve, the zero curvature, and the negative curvature. And Escher was very ingenious in showing that he could use more or less the same shapes to illustrate each of these three. If you look carefully, you see the number of the devil's feet coming together is 3 here, whereas it's only 2 there, and there are different numbers of things at the wings and so on. And so you can get these, without changing the shapes very much, you can get these 3 different geometries illustrated. This geometry illustrates various things which I've often used it in lectures on cosmology. As I said before, it's an illustration of the, this is what's called hyperbolic geometry. That's the Euclidean geometry. That's the geometry of the sphere. Hyperbolic geometry is negative curvature, and it's often, Escher did several of these, what he called circle limits. He learned about it from Coxeter, who was at the same meeting of the International Congress of Mathematicians in 1950, I can't remember exactly, 53, 54 something, where I went to this in my second year as a graduate student, and this is where I first became acquainted with Escher's work. Escher didn't at that time have these examples here, but he, let me go back to the one I just showed you. He didn't have that then, but he learnt from Coxeter, who was attending this meeting, and Coxeter explained to Escher, he said, look, it would be interesting if you could illustrate the hyperbolic plane. This is the plane that mathematicians usually refer to as the Poincaré disk. I always worry about that because it was initially due to Beltrami, and I guess people don't seem to remember it was Beltrami. He had all these different transformations. He had the Klein representation, the Poincaré half plane, and the Poincaré disk before these other people did. I'm not quite sure about Riemann, because Riemann already had the half plane, apparently, but I don't think, whether he realized it was a non-Euclidean geometry, I'm not sure. But anyway, this was the first one that Escher made. It's actually quite useful to use that one, because then you can see how you see these are the straight lines are either straight lines diameters, or else you have arcs of circles which meet the boundary orthogonally, and since it's conformal, the angles are correctly represented, and you can see how you can have lines which never meet each other. These would be parallels which actually never meet. I don't know if they call these parallels because they're parallels to infinity. And then triangles, you can see the angles don't add up to 180 degrees, they add up to something less, and all that is well understood as a piece of mathematics. But Escher had this very nice representation of it, and you can see the way you line up the figures, if I get it right. And something like that, anyway. And then this is a little bit of blurb about what it does. Now, I've also used this, or let's say this one, as a nice illustration of a kind of geometry where infinity is represented. You see the angels and devils. Actually, for that, in a way, it's easier to use this one, because you can see the fish here. The black ones are supposed to be all congruent in the geometry, so you have to imagine that this fish and that fish, they think they're the same. the geometry is such that we represent it in this way so that they get squashed up towards the edge. But as far as the fish are concerned, the white ones or the black ones regard it is completely homogeneous, this geometry. But you see also in this example, the eyes of the fish are exact circles, and these circles remain exact circles no matter how close you are to the boundary. He's done it extraordinarily accurately right down at the edge. You can look at it with a microscope and you can still see it's very, very precise right down to the edge. Now you see, this is useful. I find it useful in my discussions of cosmology because you can use the same trick for space-times. This is a two-dimensional space, but in cosmology you talk about space and time together, and 3 dimensions of space and 1 of time, and you can talk about conformal representations just the same way. And so I find it very handy. Here we see a picture, this time going up the page, and this is meant to be, well, you see, you can only represent 2 dimensions of space, but I've got this wiggly part at the back because I don't want to prejudice the whether or not the space is actually closed or not. It might be open or closed, so I've allowed for it to wiggle around at the back. But to have it look as though it's starting to be closed is useful because otherwise you can't convey the size of the space very easily. But anyway, there is the Big Bang here. The universe expands, slows down a bit, and then starts to expand again with this exponential expansion, which was recently observed and got the Nobel Prize and all that. And you see here's the Escher trick. You squash that down so it becomes a finite boundary. This is a trick which has been useful to use talking about gravitational radiation, and certainly I was in the 60s and 70s playing with that. You can also do the opposite trick, which is to expand out the Big Bang here. Escher, I was trying to find Escher representations of this. He did things rather like that. Here we have a picture as you go into the middle, and again it's conformal, and they go right down to the middle. I think you have to cut a hole and stop it for a bit, because the Big Bang is really a surface rather than the point, so you have to stop it off somewhere. But it is another an Escher representation of this idea. And here we have another illustration. So you can think of the Big Bang as somewhere in the middle there, and it's conformally represented. But it's sort of opposite trick. Here you have infinity squashed down, and there you have the Big Bang stretched out. This is a perfectly respectable thing to do in cosmology. What's not quite so respectable is this model, which is a model which I've been playing with for a long time. I think there's some evidence for it, which I won't go into here because that's not the right talk, but I just wanted to show you this picture that you can do something very Escher-like, which is join the Big Bang, the stretching out of the Big Bang to the squashing down. This is our eon, I should say, Big Bang to remote future, and then this is the next eon after ours. This is the one before ours, and they form this nice continuous stretch with all these eons going right back to infinity in both directions. Okay, that's enough of that. I haven't played with the topology of the universe. You can certainly have these homogeneous isotropic models and glue them up in various ways to make topological things. Escher did illustrate topology in various ways. Here are just some examples. See, this is a bit like a Mobius strip, but that you have to go around 4 times, I think, before you get back to your started. He did play with Mobius strips as well. And you can see these ants, or whatever they are, crawling over the Mobius strip. And they can be one way or the other way on top of each other. Nice things to examine. Okay, now let me talk about something else. I did talk about tessellations of the plane, and unfortunately what I'm going to show you came just too late for Escher. He died before I was able to, I think I wasn't quick enough off the mark. If I say he died too early, I wasn't quick enough off the mark. I wanted to show you this because it has some relation to the tiling that you see as you come in the building here. And I think I want to explain what the idea is behind that tiling. Well, this is a tiling I came across not long after Escher had actually died. I think he would have appreciated this picture. I should explain it's a well-known theorem of crystallography, or if you like, of the types of motions of the plane which I've been talking about, that the only symmetries you can have, well, you get translational symmetries, but if you have a translational symmetry that's sliding it along without any rotation, together with a rotational symmetry, then the only rotational symmetries you can have are twofold, threefold, fourfold, and sixfold. And it's quite easy to prove that. But then here you have a pattern which seems to be very uniform. It is indeed very uniform, as I'll explain. But it seems to have a fivefold symmetry. You see it's made out of pentagons, or actually four different shapes. Pentagons, these little rhombuses. You have these pentacles, a five-pointed star, and jester's caps, as I call them, sort of half stars. It's quite interesting to look at, even without knowing how it's built. If you set your eye along sort of where I'm standing, better than where you are, and you can see the things line up. Every little line continues so with infinite number of line segments. Whichever line you choose, the density of those line segments all the way along is the same. You also have these interesting decagons. All the places you see have regular decagons, regular decagons. Whenever you see a regular decagon, like this one here, well, my eyesight is not what it used to be, so I have trouble finding these things. So let me find one by looking at it close, and I'll come back to you. So here's one there. The decagons are always the same: 3 pentagons, 1 jester's cap, and 2 rhombuses, wherever they are. And whenever you find one of these decagons, it's surrounded by a ring of 10 pentagons. So I always rather like those rings. I'll come back to them in a minute. The pattern is very uniform. In fact, although it never repeats itself, it can't, that would violate the theorem, it almost repeats itself. That is to say, if you give me, say, any percentage less than 100%, say 99.9%, then I could give you a motion, a translational motion of this, such that the pattern agrees to 99.9%, and also so that it rotationally, fivefold rotation to 99.9%. And then you say, well, maybe what about 99.99%? He says, yeah, you can do that too. Any percentage less than 100%, you can find a motion which will send this pattern into itself. But it's never quite symmetric, and that's how it wriggles through the theorem. Let me explain how this is constructed. Here we have, I should say it's a sort of hierarchical arrangement. And here we have a bigger version of the same thing. Here we have do it again. This is hierarchically arranged, so another bigger version of the same thing. And here we have another version of the same thing. So that is the sort of organization. It's quite useful to show that and then ask somebody, can you find these pentagons? And it's not too easy, which is a way of illustrating how uniform it really is. Okay. Now, this pattern, I think I'm going to use the second set of hierarchy, this one here. It's a little easier to explain what I'm going to say. Here I can see the patterns more easily too. Here you have the decagon and the rings. I always like these rings, you see. I'll come back to that in a minute. But this is made out of 4 different shapes. Well, the pentagons actually, well, let's not go into that. There's another way of doing the same sort of thing. These are kites and darts. And the relationship between the kites and darts and the original pattern is this. And if you look carefully, and if I've done it right, you see each kite has the same set of lines in it, and each other kite, and each dart has the same set of lines in it. And if you match the lines, then you get this arrangement here. In fact, the only way of fitting the lines together so that you match them is to make that pattern. So these kites and darts marked with the lines that you see here can only be assembled in a non-periodic way. And so this example was the first known example where you have two shapes which will only tile the plane in a non-periodic way. You can also Escherize this, and this is the sort of thing, it's a great shame Escher wasn't able to see this. I'm sure he would have done wonderful things. I shall try and find the right spot here, which is a bit difficult. Asking me to do it. That's not bad, yeah. I don't know how well I've done it, but you can see there, these are kites and darts, but modified so as to look like birds. So this is what I mean by Escherization. This is my poor attempt at trying to do something that Escher might have done had he lived long enough. But other people have done other things like this too. So it's interesting that you can do something which I'm sure Escher would have reveled in if he'd ever had the chance. Right, let me go back to the kites and darts and so on, or to the initial, this one here. There's another way of doing it, which is these rhombuses. And again, they are related to the kites and darts with lines drawn on the rhombuses, and if you match the lines, then you get the original pattern back again. And you can do it directly between the kites and darts and the rhombuses. So it shows you can mark one of them, get to the other one, and so on. I want to try and describe the tiling outside the front of this building, because those are kites and darts. But what are the markings on those tiles? Well, that came from the following, and I better make sure I don't get these things upside down when I pull them to the side. Here we have the original pentagon pattern, and as I say, I rather like these rings of pentagons, so it was nice to mark them. There we have. These green things go around through those rings of pentagons. Now, that doesn't quite fill up the regions of the pentagons, so let's do a little more to that. I'm going to add some more green lines, and the virtue of doing this is that now I have a pattern which is really the same as that pattern, but it's a distortion of it. So you see, here we have the pentagons. You've got three different versions of the pentagons. They're very much distorted, but three different pentagons, curvilinear pentagons now. And you see the jester's caps here. There's one. Let me point this way. Here's a jester's cap, and there's a jester's cap, and so on. And so that is the same pattern, but somewhat distorted. Now, can you get these onto a rhombus tiling? Well, you can, but the trouble is that the rhombuses aren't all quite the same, so you need to add a few more lines. Having added a few more lines, you now see that every fat rhombus has the same markings on it, every thin rhombus has the same markings on it, and that is the tiling that we have outside the front. So if you want to know what it is, that's what it is. It's the rhombus tiling with all these green things on it. So the markings there. I wondered for quite a long time whether you have places where these rings close up, and there are 4 different ones where they close up, and you can see all 4 of them with different patterns on outside. But but are there any others? Well, the others would have to be ones which actually cross them. And are there any which close up and cross each other? I don't think there are in the pattern there, and I sort of conjectured that none of them did. I realized later that conjecture is completely wrong. I did find one which wiggles all over the place, much too big for the pattern outside the building here, wiggles all over the place, and finally gets back to itself. So that conjecture was wrong. So I have a new conjecture now, is that almost all of them do close. So you can certainly have patterns where one or two of them don't close, but if it's more than two, I think probably they all close. That's a conjecture. I don't know if it's true or not. Okay, that's that. And this, in fact, is the pattern that I gave to people so that they would get it right. Now I want to give you something else. I've been playing around these things quite a bit, and there are other things you can do too. Here is a set of three shapes, not just two, and they're quite simple shapes: a square, a regular hexagon, and a regular dodecagon. And these markings on them are the things you have to match. And I was interested to know if, when you match them, what do you see, do you get some feeling for the pattern as a whole? I tried this with something before and I got no feeling whatsoever. But Joshua Sokolar, I gave a talk where I mentioned this at the end, and Joshua Sokolar had a computer program which was related to this, and you can see there is a pattern over there. I'll show you the next picture, which is the next stage of the hierarchy. And I was really quite surprised how it is really a very attractive pattern. It's one of these things which never actually quite repeats. It's not quite right in that those little wiggly tiny rings ought to be exact circles. But that's the only thing that's not quite right about it. They should be, the little tiny ones should be exact circles. They actually look polygonal. Anyway, somebody perhaps could make a building and they would have these three tiles, and they'd need a lot of them to see that pattern there. Okay, anyway, that's enough of this. Now, when I told you that I did go and see an Escher exhibition when I was in Amsterdam at the International Congress of Mathematicians, and it was in the Van Gogh Museum. One of my lecturers, Sean Wiley, who taught me algebraic topology, and he had a picture of on the catalogue which had the Escher picture night and day. I haven't shown you that one, with birds flying off in different directions, and the spaces between the birds became the birds going the other way. One of them, it's a night scene and the day scene on the other side. And so I went into this exhibition, and I remember being particularly struck by this picture called Relativity, about all these different staircases and the creatures going up the staircases with gravity being in different directions. And I was really very struck by that. And of course, many of the other things he had there. So I went away trying to think I would try to do something impossible myself, not with the skill that Escher had, of course, but at least with an idea that I hadn't actually seen. And I produced things with bridges and rivers and that going off in different directions, and I whittled it down to something which I thought illustrated the impossibility in its simplest sort of reduced it to its simplest form. And I showed this picture to my father, and then he started producing staircases, buildings and all that sort of thing. And we wrote a paper where we showed some of these pictures. We didn't know what the subject was, but my father happened to know the editor of the British Journal of Psychology, so we decided it was psychology. Probably he could get it published because he was good friends with the editor. And indeed, that's what happened. So it was published, and we then sent a copy to Escher, giving reference to his catalogue and saying appreciation of his work. And in the meantime, Escher had actually produced something of a similar nature, which is this picture Belvedere, where you see the top part of the building is joined up in an impossible way to the bottom half. He, after seeing the paper we had in the British Journal of Psychology, Escher then produced his own version of the staircase, which is a very famous picture now. with the monks going around in both directions. Very beautifully done. And Escher was very generous in giving credit to our paper. This was the occasion when I said I met Escher. My father and Escher had quite a correspondence backwards and forwards, and I had Escher's telephone number. I was traveling in the Netherlands, I think in Apeldoorn, near to Barn where Escher lived, and I phoned him up and he said, yes, come along. And he said, come along for tea, which is what happened. So that's how I got to know him. But the triangle, which I'm going to show you, I'm going to say something about the mathematics that this is involved with. But before getting to that, let me show you. I was at a psychology conference, and I thought I would try and go one step better than some of these pictures and produce an invisible impossible object. So this is an invisible impossible triangle. This is also an invisible possible triangle. I'm not quite sure which one is better. You can put the two together, and maybe that works best, I don't know. Anyway, you can probably see the invisible triangle. It's not really there, but it's still impossible, even if it's not there. I was at there was a film being made for some reason about twisters and things like that. And the people, it was shown, I think it was on the BBC at one time, a long, long time ago. And they were starting this film and talking about twisters. And at one point, they finally asked me, what's it good for, you see? So I said, well, one thing you can use twisters for is solving Maxwell's equations. And then I said, well, you have to use a certain idea that I can't really explain it. It's cosmology. I can't really explain that to you, but it's... So they got very disappointed about that. So then I went home and I thought, gosh, I can. Cosmology, of course I can explain it. Here we are. You see, this is a nice way of producing that. You see, you might imagine that you have some pieces which you have to assemble to make that object. And these pieces can consist of a lot of corners like that. They're made out of wood, you see. And you make these out of wood, and you have instructions about how to glue them together. That's supposed to glue to that one, and this is to glue to this one, and that glues to that one. And you have to look at these instructions and see whether the instructions allow you to build the object, or you're going to have a little problem with it. And then I realized that actually is an element of cosmology. If the cosmology element vanishes, you just see these instructions give you a check representation of an object, and this object, you're using the freedom you have of the distance from the eye, and so that's what enables you to construct the cohomology, a non-trivial cohomology element. And if the instructions have a non-vanishing cohomology element, then that's something you can't build. If the cohomology element does vanish, then you can build it. So I thought this was a nice way into that notion of cohomology. See, it's the measure of, it's a check representation of cohomology. I was talking about this at a conference in, I think it was in Rome. It was on mathematics and art, and I can't remember, something like that. And I was talking to an American mathematician, unfortunately I've forgotten who it was, and I was explaining that my talk the next day was going to be about cohomology and how this represents that. And he said, oh, well, is there any other group you can represent? I said, well, I hadn't really thought about that. So this is the sort of, you can take the distance from the eye and you take the logarithm of it, and that gives you an additive group, so you can then talk about the cohomology in the ordinary check way. That has to be explained in more detail in the book, of course. But then he said, is there any other groups? I thought, well, yeah, there is, you know. I could think of Z2. And so, in fact, I drew this picture out, and I gave it my talk the next day. I think it's a little bit easier if I don't show you that one, but something which I developed a bit later. It's the same idea. And what is this, you see? Well, this is an idea that Escher used, and let me show you this picture here. It's the only one I know of his which I'm not sure it's quite cosmology. I haven't quite figured it out yet. But you see, on one side of the picture, I mean, Escher used this idea for other things, where you have this sort of Necker-cube paradox. The thing could be one way around or the other. You can see a cube edge on, and you may see the back of it as well. You don't know quite whether, or you see the cube and don't know whether you're looking inside or outside. And if you see this, you get it one way around, and then that tells you the rest of the picture which way around it is. So Escher has this here, and this is clearly one way around, and this is clearly the other way around, but in the middle it's ambiguous. So the whole thing is impossible because you get the ambiguity in the middle, which if you make one choice, which is this choice, that contradicts that, and the other choice contradicts this. But the thing I had here, I think Escher would have done wonderful things with this too, but you see the staircase, you could imagine walking around the staircase and, well, it's impossible. I did show it to well, there's another version of it here. I did show it to an expert on impossible objects who was at the conference. I showed him this picture, and he said, "Can you see what's wrong with this?" There's nothing wrong with that picture. "Could you make that out of wood?" You think, "Yeah, sure, I could make that out of wood." "Are you really sure you could?" You have to work, because the trouble is your eye, as you go around it, it flips to the other one without you noticing that's what's happening. So you certainly couldn't make that out of a piece of wood. Anyway, so that's that. Can you make these impossible objects? Well, that's a good question. You could certainly make the pieces. One thing you can do is this. In fact, this is a model of something which I believe somewhere at Wolfson College, it's still there, I'm not quite sure where. There is a bigger version of this. I can't show it to you all at once everywhere, because you see this is the impossibility. It's not a Czech version. This is more like one of the continuous versions of cosmology you can have. That's one way of doing it. But let me show you something else. No, that's the picture we just had, isn't it? Yes, we've done that. Yes. And wow, look, it still works. That was lined up just right, so you have, it's a possible impossible triangle. And of course, if you want to see what it really is, you give it a little twist. Well, first of all, I think the best thing is to put your hand through it, which we had, there we are. Or we give it a little twist, and then you can see what it is. Okay, well, thank you very much.
Thank you very much for this wonderful lecture. And now for the second part of the event, I'd like to please help me welcome Nick Woodhouse, who's going to take and present the awards. Please.
Shall I come down? Or?
Okay, so in a moment I'm going to call on Lavinia Clay to present the Clay Award for the Dissemination of Mathematical Knowledge to Roger Penrose. So dissemination of mathematical knowledge is a very important part of the Clay Institute's mission, alongside supporting mathematical research at the very highest level, and of course giving very large prizes. This award recognizes the achievements of people who have made exceptional contributions under both headings. In Roger's case, the award is in recognition of his outstanding contributions to geometry, relativity, and other branches of mathematics, and of his tireless work in explaining mathematical ideas to the public through popular books, public lectures, and broadcasts. Well, of course, Alain at the beginning gave a long list of his contributions within relativity, within geometry, and that is, ticks the first box very, very clearly. But he is also, as you've seen, a brilliant expositor of mathematical ideas. And it's the combination of these two which leads to the award. So we've seen some of his contributions to geometry and the Penrose tiling. But there's another aspect of his work which is really very important and which bridges the two, which is the passing from one area to another. So he begins by thinking about something impossible. So you start thinking about the idea of tiling the plane with pentagons. Most people, that might have occurred to them to think whether that's possible, and they decide very rapidly that it's not possible. Well, Roger thinks about that, and what does it lead to? It leads to the Penrose tiling, and that has an impact, a huge impact, outside the area in which he thought about it, and in that case, an impact in the visual arts and beyond. Or he starts thinking about impossible objects, and where does that lead to? It leads to a paper in the British Journal of Psychology, which is... There are other examples of this. Alan mentioned briefly the Moore Penrose inverse. Well, again, you learn at school about taking the inverse of a square matrix. Well, what about a matrix that isn't square? Well, you give that a few seconds thought, and that's impossible, so you go on. Not if you're Roger. You think about it some more, and that leads to this generalized inverse. And again, that has a huge impact. In fact, his paper on the generalized inverse is his most cited paper. It's a hugely useful tool in numerical analysis. It's had a big impact on computation. And other things where he's crossed the boundary, perhaps, it was Roger who, this one's for the computer scientists, who first made the suggestion that the Church's lambda calculus might be a useful tool in thinking about programming languages, and that again had a huge impact. But he's best known outside the scientific community for his popular books, which are wide-ranging, highly original, highly controversial, in the very best sense of being controversial, in that they provoke debate and get people talking. So they have a very unusual feature for popular books in science, in that they're addressed not only to the general public in explaining mathematical ideas, but also in engaging the public in the development of ideas. So he's putting forward his own scientific ideas, original ideas in these books in a way that many other people do not. His books have been translated into many different languages. They've sold in the hundreds of thousands. They are a remarkable achievement. Well, you may have noticed that Roger doesn't use the most up-to-date of AV technology in his public lectures. But notwithstanding that, he does have a very significant online presence. If you look on YouTube, you'll find some 30 expository videos recording lectures and interviews. And many of them have been viewed tens of thousands of times, or in one case, over 300,000 times. So that's a huge impact there. So I think it's clear that he very amply fulfills the criteria for our award, both in the contributions that he's made in the development of mathematical ideas and the incredible work he's done in the dissemination of mathematics. So I'll now call on Lavinia Clay to present the award to him.